Okay, so we're going to move on to other bases, because up until now, when we talk about the log function, I've just referred to it as log x, right? But it's really natural log of x. It's base e. And when we talk about the exponential function, it's always been e to the x. And to be fair, e is a very important base. It is, in some sense, the most natural base we have. But there's nothing wrong with, doing 2 to the x, right? Or log base 5 of x. So what happens when the base is not just e? Okay. So the first thing we want to do is figure out the derivative of, let's say, a to the x, right? Where a could be, well, a is going to represent any positive number other than 1. Right? Those are the legitimate bases here. Right, so we're using a for the base. Okay, so here's how we're going to do it. Right? We're going to use, I'd say a trick, but it's something that you should know, that if you take e to the power natural log of a, that you just get a. Right? Because after all, this is just e to the power log base e of a, and the exponential and the log cancel each other out, right? Now, obviously, a has to be positive here, and I suppose it could be 1. That does work, right? Log of 1 is 0, e to the 0 is 1. But 1 is not a legitimate base, because 1 to the x is just 1. It's not an exponential function, right? Yep. So, so notice when we take the derivative here, we can take the derivative of e to the natural log of a to the power x, right? Which, of course, by the rules of exponents, right, this is just the derivative of e to the power x times this number, log a. Log of a is just a number, right? And so we know how to take the derivative of e to any power. It's just e to that power. And then by the chain rule, we have to multiply by the derivative of x times, right, natural log of a times, right? But we know what the derivative of, 3x is. The derivative of 3x is 3. The derivative of log a times x is log a. Right? And now going backwards here, this, right, is the same thing as e to the log a to the power x, right? That's how we got this, right? We went from here to here, right? So you can go backwards. You can go the other way, right? And the log of a is still there, right? And remember, e to the log a is just a to the x. So there you go, right? So the derivative of a to the x, just copy it down here, the derivative of a to the x is just a to the x, just like you would expect for any exponential function, right? The derivative of e to the x is e to the x. But if a is not equal to e, then you also have to multiply by the log of a, which is just a number, right? Which is just a number, right? So, for example, what's the derivative of 10 to the x? Well, it's just 10 to the x times the natural log of 10. And the natural log of 10 is, 3 point something or other. But it doesn't matter, right? It's just a number times 10 to the x, right? So, yeah. Oh, what's the derivative of, how about 2 to the negative x? Oh, that's interesting. Well, the 2, right, so we know the derivative of 2 to the x is 2 to the x, so the derivative of 2 to the negative x is 2 to the negative x, but by the chain rule, we have to multiply by the derivative of negative x, and because a is 2 here, we have to multiply by the log of 2. Right, so the derivative of negative x is just negative 1 times log 2. So can we pull the negative in front? In fact, we can pull, well, no, I'm going to leave the log in the back here. So negative 2 to the negative x times the natural log of 2. And just to be on the safe side, let's put the natural log of 2 in the parentheses. Yep. So if x is not just x, but a function of x, like sine x or even just negative x, you need the chain rule as well. So maybe let's write this down with the chain rule. The derivative of a to the power u is a to the u times the natural log of a times the derivative of u, and that's the chain rule part. So that's the most general version of the exponential rule. Obviously, if a is e, then log of e is 0. So we can do that very quick. What's the derivative of e to the x? Well, it's e to the x times the natural log of e. And the natural log of e is, oh, did I say 0? I meant 1. Natural log of e is 1. So e to the x times 1 is e to the x. Okay, I'm going a little faster. Yeah, natural log of e is not 0. It's 1. Phew. Okay. All right, so yeah, so this is, again, this is one, eventually you should get used to that, right? So what if we want to do the same thing with logs? We want to take the derivative of, so find the derivative of log, but instead of base e, let's use any base a of x. Right, so what's that going to be? Well, in some ways, we know what to do when we want to change log base a of x to some other base, right? We use the change of base formula. So let's say we want to change this to base, let's call it b, base b of x. This is just going to be log base a of x divided by log base a of b. And now that I think of it, I think I wanted to go the other way, right? I wanted this to be an a here. So this should have been an a because that's what we have. So this is log base a of x. And this a then can be some other base, but it has to be the same. Oh, and that makes this an a as well. Okay, so I'm just erasing everything here. Okay, so this will now be a b, this will be a b, and this will be an a. So what b should be used? Well, the only log we know the derivative for, way up here, is natural log, right? Base e. So my b should just be e. So in other words, this is going to be log base e of x, it's x, divided by log base e of a. Or better yet, this is just natural log of x divided by the natural log of a. Right. So that's what I'm taking the derivative of. Taking the derivative of log x divided by log a. Right. Now this is derivative. So this is the derivative of a quotient. We can apply the quotient rule if you want. That's, that shouldn't be hard. But we shouldn't have to because notice a is a number, right? A is just a constant. So log of a is a constant. And so we can take that outside the derivative. Constant times function rule, right? 1 over log a times the derivative of log x, right, over 1. But the derivative of log x, well, hopefully by now you know that it's just 1 over x. And so there's our derivative. It's just 1 over, I'll put the x in front, x times log a. See, the problem with writing it this way is that this is a little bit ambiguous. Log of ax, are you taking the log of a times x? No. You're taking the log of a and then multiplying by x. So I would put parentheses here. But if you put the x in front, then you don't really need parentheses, right? So, yep, let's go back and put that rule up here. If you're taking the derivative of log base a of x then it's still 1 over x, but unless a is e, you should divide by the natural log of a as well. So there you go. Again, it's make sure you know that. It will come in handy in Calc 2 as well. Okay. Oh, and maybe, you know, there should be a chain rule version to this. So if you want to change this x to u, let's say. Okay. So we'll make this a u. And this is a u, but then there's a chain rule multiplied by the derivative of u. Okay, so that's the most general version you're going to see here. Right. Oh, so I guess the only thing we haven't talked about now is what do you do when you want the integral of a to the u? Well, let's start with a to the x. We can do the substitution later. What's the integral of a to the x? So we can use the same trick that we did for the derivative here, right? We can write this as the integral of e to the log of a to the power x, right, dx. And of course the x can multiply the log a, so this is e to the x times log a dx. And now just use a substitution here, right? U is going to be the exponent here. U is equal to x times log a. And the derivative of u is just going to be log of a times, sorry, that's an a. Let me try that again, a little bit sloppy. Log of a times dx. Okay, so, yep, so to do this substitution, this is just going to be e to the u, and then, right, to put in the log of a dx, I also need to divide by log of a on the outside. So we have 1 over log a, the integral of e to the u, and then this here is just, oops, sorry, du. Okay. Yep, times du. So the integral of e to the u du, of course, is just e to the u plus c. So you get 1 over natural log of a times e to the u plus c. But u, of course, was x log a. And e to the x log a, so e to the x log a divided by log a is really just a to the x. So this is a to the x divided by natural log of a plus c. So here's the rule, right? The integral of a to the u du is just going to be a to the u divided by natural log of a plus c. And that would incorporate any substitution you might need, right? In fact, we already did that. There's a substitution here, for example. Okay, so I think these three rules here, these three rules are all you need from this section. As far as I know, I think that's pretty much all we're going to do here. All right, so maybe some more examples. Okay, so I guess we'll do an easy one here. Suppose we want the integral of 5 to the power x squared dx. Oh, I don't think we can do that one. Hang on. Yeah, so e to the 5 to the power x squared times x dx. That we can do. That we can do. Well, right. So in this case, I'm going to just say a is 5, right? And u is x squared. So du is 2x dx. So yeah, we have the x. We don't have the 2 here, but we can always multiply by it. So let's do that over here now. This is 5 to the power x squared x dx, we need to multiply by 2 and divide by 2. And that makes this into du, and this becomes 5 to the u. So we just get 1/2 the integral of 5 to the u du, and the integral of a to the u is, well, a to the u, so 5 to the u, but divided by natural log of a, which is 5, right, plus c. And then just change u back to x squared, right? So this is 5 to the x squared divided by 2 log 5 plus c. Oops. Yeah, let me change color here. So that's the answer to this problem here. Okay. Yes, so there's one other type of problem. I think, I'm gonna start over here. So let's just recap, right? So starting with the usual natural log and e to the x, and then just using some basic properties of inverse functions, we were able to get these 3 rules here. So these 2 involving either a to the u or log base a of u, and then we do the integral of a to the u. Okay, so let me scroll down one more time slowly, right? So we calculated all this, and that gave us these 2 rules for derivatives, the exponential and the log, right? And then we got the derivative of, that was this. That was up here. Hang on. Then we got the integral of a to the x, which is a to the x divided by log a. Okay, yeah, so don't get confused. You don't multiply by log a here. That's when you're taking the derivative. When you're taking the integral, of a to the x, then it's still a to the x, but then you divide by log a. Right. So don't get the integral mixed up with the derivative. Okay. And you also divide by log a when you're doing the derivative of log base a. So again, these 3 rules, ideal that you should know them. Obviously, if you don't remember them, you can look them up. If you have to look up every time you take a derivative, you're going to be wasting a lot of time. So this is why we actually ask you to memorize these, because they come up often enough that it's a real pain to have to look them up every time. They're ones you should know by heart. So I hope that helps. Okay, so now I'm going to clear all this, and we're going to start fresh with a new problem. And let me write it down, so I'm not going to waste time writing it down here. Okay, here we go. This is f of x is x to the power x, and we want to find the derivative, right? So, we want to find the derivative of x to the x. I'm not going to write it here. I'll write it down here. We want to differentiate or take the derivative of x to the power x. How do we do that? Okay, so we can't. It's tricky. It's one that you have seen before, sort of, but maybe not in this context. Okay, so here's what not to do, right? Here's what you cannot do. Right? You can't use the power rule, because in the power rule, we're assuming that this n is a number, right? It could be x squared, x cubed, x to the 1/2, x to the negative 18.5, right? It could be x to the pi. But as long as this is a constant, then, of course, then you just take the derivative, as usual, n times x to the n minus 1. But that's not going to work here, right? This is not x times x to the x minus 1. Well, that would imply that this is x to the x, right? Because it's x minus 1 plus 1, right? Which is just x. But that's not the answer, right? It would be nice if the derivative of x to the x was x to the x, but no, it's not, right? It is true, of course, the derivative of e to the x is e to the x, but not x to the x. Well, there you go, right? So you might say, of course, I can't use the power rule here because, yes, this n is not a number. It's a variable. It's x, right? So you might think then I just have to use this other rule of a to the x, which is just a to the x, right, times log of a. But now we run into the other problem. Now the base is a number. The a has to be a constant, a number, right? It could be 2 to the x, it could be e to the x, it could be 21 to the x, it could be any number to the x, but that a cannot be a variable. It cannot be x, right? So, yes, so we cannot apply this rule. In other words, the derivative of x to the x is not x to the x times log x. Yeah, so that does not work also, right? So, yeah, we're stuck, right? We can't use this rule, and we can't use this rule, because both rules imply that either the exponent or the base is a constant, and neither of them are constants here. Okay, so, yeah, so we're kind of stuck here. We know what it's not equal to, so what does it equal? Okay, well, like I say, it's a little tricky, but it's a technique that we have seen before. We're going to use, oops, if I can spell, logarithmic differentiation. Differentiation, right? In other words, we're going to take the logarithm first and then take the derivative. Okay, so I'm going to write, instead of writing f of x here, I'm just going to write it as y. Okay, so we have y equals x to the x, and remember, our goal is to get the derivative of y, right? Equals what? Well, before you try to take the derivative, it might be helpful to take the natural log of both sides. We could use any base, but trust me, ln, natural log, works best here. Okay. So we have natural log of y equals natural log of x to the x. And now you might think, but wait a minute, if I'm taking the derivative of both sides, I'm going to use the chain rule here, and I'm still going to have to take the derivative of x to the x. Of course. But remember, the whole point for doing this is to use the rules of logarithms. And one of the rules for logs, I'll put it way down here, remember, the log of a to the power b was b times natural log of a. The exponent can come in front. And that's true even if b is not a number. It's true even for a generic variable like x. We can bring the x in front. So that's the key. This is going to be x times log x. Okay, and let me just bring that down here so we can work with that. Times log x, right? So now, having gotten x out of the exponent, yep, now we can take the derivative of both sides. Okay, so on the left side, the derivative of log y is just 1 over y times the derivative of y. The right side, we have to use the product rule, right? So it's not 1 times 1 over x. Right? Oh, I don't need parentheses here, right? It's going to be first times the derivative of the second. Well, the derivative of log x is just 1 over x, right? Plus second times the derivative of the first. Well, the derivative of x is just 1. So if it's all the same to you, oops, I'll just leave that as 1. And let me get rid of this rule because we know the power rule here for logs. Okay, all right. So, yes. So where are we now? We have, on the left side, we still have 1 over y times the derivative of y. And on the right side, we have, well, x over x is 1, plus 1 times log x is just log x. Okay. Well, the only thing left to do now, right, we want the derivative of y. Sorry, I erased the 1 here. I wanted to move it over a little bit. Right, we're trying to find dy by dx, right? What's the derivative of y with respect to x? So, well, all you have to do now is multiply both sides by y. Right? So y over 1, and do that on the right. And so on the left side, y divided by y is 1. They cancel. And we get our derivative, dy by dx, equals y. But remember what y was. Y was originally just x to the x. So I can replace this y with x to the x times 1 plus log x. And there you go. Right? So that's the derivative of x to the x. Yep, let's write it up here so we have it for posterity. Right? So if the original function was x to the x, then the derivative will be x to the x times 1 plus natural log of x, right? Yep. So remember, if you were to apply the power rule inappropriately here, because n is not a number, you would get x to the x, which we can see is wrong, right? You're missing the 1 plus log x. And yeah, you can see that if you applied the exponential rule, you're a little bit closer, right? You have x to the x log x, but you're missing the 1 plus log x. In other words, you're missing another x to the x term here. So yeah, these rules kind of get you close, but you're missing something, right? So yeah. So the only way that I know how to do this is logarithmic differentiation. Take the log first, like we did here, right? And then use the power rule for logs, right? Bring the x in front, and then take the derivative of both sides. And this is what you get. So yeah, when you have x in both the base and the exponent, logarithmic differentiation is the way to go. I'm crossing it out. So that should help. And I think maybe we should do one more example of where this comes up, maybe in a more practical problem here. So yeah, so I'll put up another example. Okay, so we have $2,600, and we're going to deposit that in, let's say, a savings account or some investment account, earning 5% interest that's compounded quarterly, right? So 4 times a year. And we want to find the amount of money that's in the account after 15 years. So in other words, we make a deposit and we just leave it sitting there for 15 years, right? Yeah, so we don't make any withdrawals or any extra deposits or anything. So that's part A. Part B, suppose the interest is compounded continuously instead of quarterly, right? Then how much is in the account after 15 years? And finally, find the rate of change of the value of the account after 15 years. I know it's a little sloppy, but so I'll read it again. Find the rate of change of the value of the account after 15 years. Because that's part C. So let's go back to part A. So for part A, it might be helpful to know that the amount of money after t years is given by p times 1 plus r over n raised to the power n times t. Again, it's probably something, I'm sure you've seen this before, but you may have forgotten it. You don't have to remember this. I mean, if you're going into finance or business, or banking, then you definitely need to know this. This is like fundamental. This is very basic. But if not, if you're going into engineering, you probably won't need this. And besides, like I say, you can look it up. Okay, so suppose we're given this formula here. Right, we're given this. Right, so what do? Essentially, part A is just plugging in numbers, right? So P is the principal. That's what we're starting with. That's the $2,600. R is the interest rate, right? It's not 5, right? R has to be a decimal, right? So this would be 500%. Not likely, right? So 5% as a decimal is 0.05. N is the number of compounding periods per year. Quarterly means 4 times a year, so N is 4, right? And T, of course, well, it's the number of years, which in this case is 15. So you plug all that in, and you just get a number, 0.05 over 4 raised to the power 4 times 15. And, yep, that's going to be 2,600 times 1 plus, well, 0.05 divided by 4, I think is oh, now I don't know what it is. I think it's 0.0125, right? 0.0125, yep. Well, don't take my word for it. Use a calculator. Yep, okay, so 1 plus 0.0125 is 1.0125. I think it's right? And then 4 times 15 better be, oops, sorry about that. Better be 60, right? This stylus has a, there we go, 60, okay. All right, so, yep, just plug that in your calculators. Where's the exponent key? 60. Yep, so this is going to be more than double. 2,600 times 2.10718. And I think we get, supposed to be $, $5,478.67, rounded to the nearest penny. There you go. So that's how much you have in the account after 15 years, right? So it more than doubles, just slightly more than doubles here. Okay, so that's part A. What about part B? Suppose the interest is compounded continuously. Well, if you're compounding continuously, you have a slightly different formula. The amount of money after T years is just PERT, right? P times E to the power RT. What happened to N? There is no N. N is the number of times you're compounding per year. If you're compounding continuously, you're compounding every moment in time. How many moments are there in a year? That's kind of maybe a philosophical question, but effectively, there are an infinite number of moments in a year, right? So you can't just replace N with infinity. That doesn't work. You can take the limit as N approaches infinity, and I'll show you that later, how you can actually get this formula by letting N just go to infinity. But before we do that, let's just get the answer here, right? So again, N is not equal to infinity, it approaches infinity. All right, so just plugging in the numbers here, yeah, what do we get? We still get 2,600 for P, and then times, I don't need parentheses, this is just times, e to the r, which is 0.05, times t, which is 15. Okay, so just use your calculator, and you get your answer. Okay, so I get $5,504.20. There's no rounding issues here, I think. Okay, so you can see it's, oh, I don't know, $26 more. When you compound continuously, you do get more money, but surprisingly, maybe not that much more, just, you know, 26 bucks more. Not a big deal, right? Yeah, so that's as opposed to compounding quarterly. You do get a little bit more. Anyways, let's go on to part C here. Find the rate of change of the value after 15 years. So rate of change, yeah, you know what that means. Rate of change of the amount. Well, value, so the word value here is how much is in the account. What's the amount of money in the account, right? So yeah, we just want the derivative, right? And remember, this is with respect to t. R is a constant, right? So by the chain rule, we multiply p times r times e to the rt, right? So in this case, it's really just this multiplied by r, right? So everything's the same here. It's still 2600, but now we just multiply by 0.05. 15, right? So this is just going to be 0.05 times $5,504.20, which I think you can just divide by 20, right? Divide by 20, and you get 275.21. So this is going to be approximately $275.21. So that's the rate of change of the value of the account. So what do we mean by that, right? So after 15 years, this is how much money you have, right? After 15 years, if you're compounding continuously. Sorry, 15 years. And this tells you how quickly your amount is changing. This is how much money you get per year, right? This is a rate, so it's per year. So knowing that, we can approximate how much money you have after 16 years. After 16 years, well, after 15 years, you have $5,504.20. And per year, so 1 year later, you get 1 times $275.21. So let's add those up. 5504.2 plus 275.21, and that gives us a grand total of, oops, sorry, the stylus does not work very well. Okay, so $5,779.41. Yep. There we go, right? So that's how much you would expect to have after 16 years. Okay. But do you? Not really. Not exactly. This is pretty close. It's a good approximation, but that's not how much you get. If you want to know how much you have after 16 years, well, go back to the formula here. Go back to this and just replace the t. Instead of 15, make it 16. Okay, so let's do that, right? So the amount after 16 years equals, well, 2600 times e to the 0.05 times 16 instead of 15. So plug that in your calculator. And I come up with $5,000, right? So $5,786.40, or maybe 41 cents if we round up. Yeah, okay, we'll round up. The bank probably rounds down. Right, so that's the actual value. Compare that with our approximate value. Remember, this is only approximate. Although technically this is approximate too, but you're rounding to the nearest cent. That's a lot closer, right? So this is what you really have after 16 years. This is what you approximate. So what's the difference here? It's 5,700 something, 79 to 86. So that we're off by $7. We're off by $7. Which, I mean, some people might not care about $7, but I do. That's a lot of money. So if you do this thing here, you're rounding, right? So what's the deal, right? What's if this is the sort of exact and this is the approximate, what's going on here? So a graph might be helpful here. So I'm going to draw the graph, and we'll see what's going on. So here's t, here's time, and here's the amount of money, right? We're starting with $2,600. Let's say it's right here. This is 2,600. So my scale is obviously going to be way off, but that's fine. And this is an exponential function, so it is growing exponentially. And this might be not very exponential, but let's say that that's the graph. And let's say, yeah, right here, this is t equals 15 years. And let's say this is t equals 16. Obviously, I'm changing the scale a little bit, but I need to make a point here, right? So if you plug in 15, you go over here and you get the exact amount. I forgot what that was. What was it? Oh, 5504, right? 5504 and 20 cents. 5504 and 20 cents, right? So that's what you get exactly after 15 years. All right. So this amount right here is what you get when you plug in 16. So let's do that way over here. You get 57.86 and 41 cents, right? Okay. So where did I get this amount? Oh, I'm sorry. I didn't want to use blue here. I'll use red. Where did I get this amount from, right? So I got it from knowing what you got after 15 years, and then I got the rate of change, meaning at this moment, at 15 years, we expect our money to grow $275 per year. So I just added 275, right, times 1 year. If I want to know what's after 2 years, I'd have to multiply this by 2, or 3 years, multiply it by 3, and so on, right? But we just did 1 year later, right, to t equals 16 years. So this is sometimes called, right, the tangent line approximation. Approximation, right? So you can use the tangent line to get an approximate answer. Here's how it works, right? So this rate here is the slope of the tangent line at t equals 15. So I'm going to do my best to try to draw a tangent line, something like this. Yep. So the slope was 275 point, whatever it was, 21. Right. So we're using the tangent line to approximate the value at 16. And by doing that, we're getting this value right here. What's the actual value? Up here. Right? So you might have to zoom in a little bit to see the difference. It's not much difference, right? As I said, it's $7 difference here. Okay. So here's what I'm going to do. I'm going to zoom out here a little bit, right? I'm going to take this picture, blow it up, make it a lot bigger, and then you'll see what's going on here, right? So when you blow this picture up, you get this curve, and you get the tangent line right here. Again, I'm a little sloppy here, right? And then let's say this is, right, this is what you get for the tangent line approximation, right? So the y-coordinate here, that's going to be the 57.7941. So 57.7941. However, the exact value, when you go up here, this is the 57.8641. So this difference here, this is your $7 difference. That's sort of the error that you get when you approximate using the tangent line. Okay, and I don't know, is $7 an acceptable error? I guess that depends on your point of view. For me, no, of course. I mean, you know, if my bank shorted me $7, I would complain. I'd say, hey, you're missing $7. I'm, you know, but, yeah. But again, that's banks use this formula. They get the exact value. They don't use tangent line approximations. But, you know, if in some cases the approximation might be much better than this. You know, for example, if you want to approximate, use the tangent line approximation not for 16 years, but say for, you know, 15.03 years, now the difference is going to be minuscule. Now you might be off by, you know, a few pennies or something. So that's the idea of using the tangent line to approximate, right? Using this rate here to approximate. And the key is that you can't go too far away, right? Going 1 year is already, a pretty big difference. If you go 2 or 3 years, you can see what's going to happen here, right? So this is 1 year. If you go 2 years away, this curve just gets much, much further away. So now your approximation might be completely unacceptable here, right? You might be off by, $40 or something, right? And the further out you go, you might be off by thousands of dollars. So yeah, we're using a tangent line to approximate, and as long as we're not too far away, right? In other words, if you look at the green curve and the red line, yeah, they're off a little bit here, right? Tiny little bit, but not much, right? So you get a better approximation the closer you get to the original point, which in our case was 15, right? We wanted to plug in 15 years. Oh, sorry about that. 15 years was the original question, right? How much after 15 years? Okay, so that's the idea of tangent line approximation. And in fact, I think I'm going way above and beyond what we wanted to do here. Basically, can you use this formula to just use this formula here to plug in numbers? Sure. And can you use this formula? And can you take the derivative of a formula, assuming, of course, that, the t is the variable, p and r are constants, and, of course, e is a constant. Yeah, I mean, look, that's basically it. Let's do one more. Right, so this is a more practical problem. Let's do a generic calculus problem here. Scroll up. Okay, so let's write down the question. So suppose we just want to take the derivative of log of the square root of x squared plus 9. Okay, so parentheses are optional, but let's just make it clear. We're taking the log of the square root of x squared plus 9, right? Well, so first of all, this is what base. So you should know by now, when you don't see a base, it's the common logarithm. It's base 10, right? It's not e, because e is, right, natural log, ln. Okay. And while we're at it, we can change the square root to x squared plus 9 to the 1/2. Oops, that's a 9. The 1/2. Right. And so you may remember the formula for log of any base, right? Well, if not, feel free to look it up, right? Here it is again. Log base a of x is just going to be, even I'm forgetting. It's going to be 1 over x times the natural log of a. Okay, I think that's it. Of course, this is not just x anymore. This is our u. This is our g of x. So we need to apply the chain rule. But before we do that, this is an exponent. Why don't we bring that in front of the log? In fact, since it's a constant, we can bring it in front of the derivative, right? So this is just going to be 1/2 times the derivative of log base 10 of x squared plus 9. And now there's no way to split this up, right? We can't go any further here. So here we're sunk. Here this is the g of x, and we just use the chain rule here, right? So this is just going to be 1 over, there's a 2 in the denominator, there's a natural log of a is 10 in this case, so natural log of 10. And then the x, in this case, is x squared plus 9. But by the chain rule, we multiply by the derivative of x squared plus 9, which is, of course, just 2x. We pulled it over here on the right? So we have a 2x in the numerator. In the denominator, we have 2 log 10 times x squared plus 9. Okay, well, we can cancel the 2's, right? 2 divided by 2 is 1. And so I think we're just left with 1 over Okay, I'll leave the natural log of 10 in front. I was going to pull it in the back, but it doesn't matter. Times x squared plus 9. And, oh, not x, not 1, x, right? Oh, yeah, there's still an x in the numerator. Yep. Boy, I almost missed that. Yep, there's an x in the numerator. Okay, so x divided by log base 10 of x squared plus 9. And there you go. That's a pretty reasonable example. Again, it depends on if you know this or not. If you don't know the formula for log base a, it's right. Then you need either the change of base formula for logs, or this incorporates that. So this is probably one to know, along with the other two that we talked about earlier. Anyways, so that's it. That's it for, well, this video. That's it for the course. We're done. Right? So this was section 5.5, I think, and that's as far as we're going to go. So, so I hope you enjoyed this as much as I did. I have to say, I really, really miss teaching. This, I mean, look, this is nice that I can do this, but I miss your questions. And, I make these little mistakes here, and I can't guarantee that I catch all of them, right? This x over here, I almost missed that here. So I'm sure a lot of you would be keeping me honest in class. You'd say, hey, you forgot the x. And so, yeah, I miss that, and I miss your questions. I really wish I could be doing this in front of a class instead of in front of a screen here. So, yeah, I mean, I miss your real-time questions. You're welcome to ask anything by email. You're welcome to ask, well, I guess it's by email for now. So again, this might not be ideal, but hopefully I go through enough examples to get you through the homework and any questions that could be on the test. Again, the test is not going to be anything that much harder than these. I know that last one was a little bit challenging, and so this test, I might do something roughly the same. But to be fair, most of you did okay. So I'm not going to make it any harder than the last test, but I don't think I'm going to make it that much easier either. So for your test 4, which, maybe I should remind you, just covers sections, so chapter 4, sections 2 through 5, and then chapter 5, we covered 5 sections, 1 through 5. So I guess that's 9 sections, which is a lot, but I think these last 5 go pretty quickly. It's just getting used to logarithms and exponentials. And I mentioned, I think a lot earlier, that some books use early transcendentals, so they would do all of this way back in chapter 2 when we first started talking about derivatives. They would go through the derivative of e to the x and log x and all those. But I think I like it better putting it off to the end, at least to the end of Calc 1. So so I'm sure there was something I'm forgetting to tell you, but you can always ask later. Anyways, I hope you enjoyed this class. I know I do. This is one of my favorite classes to teach, and I'm sure you'll all do very well. And when you take Calculus 2 with either with Professor Karnowski or Professor Doppern in the summer, that it'll be probably just as enjoyable, if not more. They will be vastly more entertaining than I have been. But this has been a real pleasure, and I'm still getting used to this system here. You can see when I scroll back and forth, I know it's kind of irritating, and also my pen has a little button that controls the up and down thing. So when that happens, I blame my little stylus here, but little things like that, I plan to go and do the videos for the first part of the class later, but obviously not in time for, say, the final. For the final, I do hope to do, a good review video. If I can somehow find a way to get on WebEx, I might try to do that, and we can have sort of a live session. I can't guarantee that, but we'll see how it goes. Anyways, this is it. This is it for the course, and I hope you enjoyed and as much as I did. And I know I'm not going to see you, most of you, again, and until the fall, maybe. So I hope. Happy studying, right? So do the problems in these sections, and if you have any questions, please feel free. Until I do the review video, I just wish you happy studying and enjoy. Don't work too hard, but it's hopefully this is not the craziest stuff in the world. All right, so take care.